Welcome to The Explainer. Today we're taking a seriously epic journey, scaling all the way from the cramped, visceral reality of a Mars-bound rocket right up to the mind-bending relativistic physics of light-speed travel. We're going to break down the exact science and engineering it actually takes to leave Earth and cross the cosmos. To really grasp our future in the stars, we need to zoom out. We're starting close to home, figuring out how we survive a trip to Mars, and then expanding out to the theoretical limits of space-time itself. Here's our roadmap for the journey. Life aboard the Starship, nuclear engines to Mars, the interstellar weight calculation, engines of the far future, and finally, illusions at light speed. Let's get right into it.
Section 1. Life aboard the Starship and surviving the journey to Mars. Because before we can even think about bending the laws of physics, we literally just have to deal with keeping fragile human biology alive. Let's look at the gritty reality of interplanetary travel on a vessel like the SpaceX Starship.
You know, NASA actually ran studies to figure out exactly how much room a person needs for a 2.5-year Mars mission without entirely losing their mind. The absolute minimum? 25 cubic meters. Just try to picture a standard shipping container. That's it. That is the total general living space required per person on this journey.
And because we're packing light, luxury is totally out the window. Water is incredibly heavy. If we didn't recycle, a massive chunk of our payload would just be water weight. So following the standard set by the International Space Station, 93% of the water you drink on this trip will be rigorously recycled from wastewater, sweat, and, urine. You'll be drinking your own filtered pee, because out in deep space, it's a strict requirement for survival.
Picture taking an elevator up this massive ship. The whole layout is driven entirely by physics and practicality. You'd start way down in the unpressurized cargo hold. Got to keep that center of gravity low for landing on Mars. Moving up, you pass through the noisy hygiene and storage decks, squeeze past highly claustrophobic crew bunks made for up to 20 people, and finally hit the flight deck at the very top. It's designed specifically to keep the crew safely away from those intense pendulum-like swinging forces when the ship flips to land.
Which brings us to Section 2, nuclear engines to Mars, and our quest for faster travel. Living in those cramped, highly confined conditions for a standard 9-month trip is absolutely brutal. It exposes the crew to radiation and severe psychological strain. We desperately need something way faster than our traditional chemical rockets.
Now, to get that speed without filling the entire ship with giant fuel tanks, aerospace engineers obsess over this metric called specific impulse. In simple terms, it's a measure of how much kinetic energy you can squeeze out of your propellants per unit of weight. The higher the specific impulse, the less fuel you have to bring. That frees up space for critical cargo and lets you travel much, much faster.
So we basically have two primary nuclear options to pull this off. On one hand, nuclear thermal engines use fission heat to expand liquid hydrogen, giving us high thrust and double the specific impulse of chemical rockets. The catch? Storing liquid hydrogen for a long time is notoriously difficult. On the other hand, we've got nuclear electric engines. These power super-efficient ion drives using storable noble gases like xenon. They offer astronomical specific impulse, up to 10 times greater, but the thrust is incredibly low, meaning it takes a long time to build up speed. Honestly, a hybrid of both might ultimately be our ticket to Mars.
But what happens when we want to go even further? That brings us to Section 3, the interstellar weight calculation, and when to launch for the stars. Once we master our own solar system, the next logical target is Alpha Centauri, 4.4 light-years away. But the second we try for it, we crash into this wild logistical paradox. Think about it. Why would you launch a Starship today if a much faster one, built 50 years from now, is just going to overtake it mid-journey? It makes absolutely no sense to spend centuries on slow rockets if waiting a few decades for better technology means you actually arrive sooner. Nobody wants to launch on a generational ship only to have their great-grandchildren get passed by a ship that left Earth half a century later. Finding the right balance between the Starship's speed and the development time of the technology is paramount.
We've got a few real possibilities on the interstellar menu. Contained fusion could get us there in about 90 years at 10% the speed of light. Antimatter engines, literally annihilating protons and antiprotons, could push us to 50% light speed, cutting the trip down to just 9 years. But the most realistic near-term option? A laser light sail. By blasting a massive laser at a sapphire-coated sail, we could push an unmanned probe to Alpha Centauri in 45 years, requiring no onboard fuel whatsoever.
Moving on to Section 4, engines of the far future. We're talking antimatter and artificial black holes. To truly shrink the galaxy down to human lifespans so we can travel in person, we have to look way past fusion and sails. We're looking at engines that convert almost 100% of their mass into raw, unadulterated energy.
The most awe-inspiring subliminal engine physics can dream up is the Kugelblitz drive. Okay, get this. It's a starship powered by an artificial black hole made entirely of densely concentrated laser light. It would be no larger than a single proton, yet it would weigh 600 billion kilograms. That's the mass of 2 Empire State Buildings in something you couldn't even see. This absurd little singularity would pump out nearly 160 petawatts of Hawking radiation. That is 10,000 times the entire world's power consumption, which we would capture to propel our ship forward. It's wild.
Finally, Section 5, Illusions at Light Speed and the Visual Physics of Extreme Velocity. As these incredible future drives push us closer to a significant fraction of the speed of light, you have to ask a very human question. What would you actually see if you looked out the window?
Well, as we accelerate, we'd experience the aberration of light. Have you ever driven fast through a really heavy rainstorm? Even though the rain is falling straight down, your speed makes it look like the water is hitting your windshield directly from the front. The exact same thing happens with light in space. As you move faster, the starlight of the galaxy literally appears to bend and focus directly ahead of your ship, changing the very geometry of the sky around you.
The visuals at these speeds get completely trippy. The sky physically appears to contract into a blindingly bright spot right in front of you. And because you're catching up to the light waves ahead of you, the Doppler effect shifts the forward stars to a brilliant blue, while stars behind you shift to red, until eventually the universe behind you just goes pitch black. And if you flew past a planet, it wouldn't look squished like you might think. Because the light from the back of the planet takes slightly longer to reach your eyes, it actually appears physically rotated. It's a mind-bending illusion called Terrell-Penrose rotation.
But the strangest effects are physical, not just visual. Because your trajectory through space-time is totally different from Earth's, you experience serious length contraction and time dilation. From your seat inside the ship, crossing the galaxy might feel like it takes only a few seconds, with the universe essentially folding around you. But back on Earth, thousands of years will have ticked by. You literally become a time traveler, moving purely into the future.
Now, there is a catch. The ultimate cosmic speed limit. No matter how much energy we pump into our engines, no matter how long we hold down the accelerator, our ship will remain completely motionless relative to a beam of light. Light is always going to escape you at the exact same speed. We can never actually reach the absolute speed of light through space.
But Einstein's general relativity gives us this absolutely spectacular loophole. While we cannot move through space faster than light, nothing prohibits space itself from doing so. What if we don't move the ship at all? What if we use a warp drive to bend and propel the actual fabric of space-time itself around a completely stationary starship?
And that leaves us with a pretty staggering question to ponder. If human ingenuity actually allows us to fold reality and bypass the limits of light entirely, what kind of universe are we stepping into? What happens to the one we leave behind? If we master space-time itself, what are the true boundaries of human exploration? Thanks for exploring the cosmos with me today. Keep looking up, and I'll catch you in the next explainer.